So
4-bit adder. Okay.
So that last carry, where would that go?
That's just your, when you're adding,
For example, if you had one,
if you were adding numbers here, what do you do with that number? Let's say this was 5, right? What's one, say 7. 1 and 7, 8. 8 and 3 becomes what? 11. What do you do with that digit? That becomes part of the number.
Yeah, but
Yep.
you ignore it.
No?
Like we did
No,
before.
no, that becomes part of the number for the adder for now.
And the adder does
Yep,
actually.
yep.
Because remember when we did the beginning, we just ignored it.
So that becomes part of the number. Now, what does the inside of that looks like? Graph paper.
So it's like a multiplication, it's actually just like a stack of adders.
Is what?
A multiplication.
Well, let's see. Let's see what we have. We have 3 inputs. I'll call them AN, BN, CN minus 1. Why minus 1? Why do I use that notation? Anyone?
Carry it from the
Previous, the one before it, right? So that's my thinking why I use N and CN. And let's look at it. Let's list all the options. Could be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. My output is going to be what? Is going to be the sum and the carry for the next state. Now the sum is what? What's 0 plus 0 plus 0? Zero and carry of 0. What's 0, 0, and 1? 1, no carry. What is 0, 1, 0? 1, no carry. What is 0, 1, 1?
10, right?
0 and carry 1, yep. What's 1, 0, 0? 1, carry 0. 1, 0, 1, that's a 2. 0, carry 1. 1, 1, 0. 0, carry 1. And 1, 1, 1.
11.
1, carry 1, yes. So that's what each one of these, I'm trying to build what the inside of each one of these is. We have the carry coming in. The first time you connect it, the carry is 0 because the first digit you add, there is no carry. After that, the carry goes to the next state. And the carry from this to the next one, and the carry from this to the next one. Each one of these is called a full adder, and this is the inside of each one of these. Not the 4, each one of them. Then when you connect them together, cascade them together, you have a 4-bit adder. If you take 8 of them, you have an 8-bit adder. If you take 12, you get 12-bit adder. So what the inside looks like then? Can we build it? Sure we can. We can simplify what the logic for it. Let me go back to the K-map, do a K-map for each one of these and see if I can simplify it. Build them. And that's what the inside will look like.
So you're doing K-map?
K-map is the easiest way to simplify. So I'm going to do 2 K-maps. One for SN and one for what? And one from CN. And I'm going to build both of these. Oh, wait a minute. Shoot. That's the 3 input K-map. Ah. I didn't realize till I finish here. So the bottom 2 are gone, right? I don't have 4 inputs. There goes my whole whiteout. 3 input. Fell asleep there. A and B, C, see, I shouldn't record that one. When I'm doing this, I'm telling you, I'm probably 5-6 steps ahead thinking about the next example in my head. I'm just going through the motion with this, so sometimes I fall asleep. I go, uh-oh, I need to do this. So Sn, let's write them. Let's put the values. 0, 1, 1, 0, 1, 0, 0, 1. Not nice. There's nothing you can do to simplify it. Nothing. The carry is not bad. 0, 0, 0, 1, 0, 1, 1, 1. I can go this way. I can go this way. I can go that way for the carry to group all 3. So if I look at this one here, the outside, A is 1, B is gone, so AC. If I look at this one, that's BC. And if I look at this one, that's AB. Sn now, I gotta group this by itself. A naught, B naught, C. A naught, B, C naught. ABC. And A, B naught, C naught. And I can design the inside of each one. So if I pretend this is my box, what's in it? Let's say we have the 3 inputs here. Now let's make it nice. See if I can fit it there. This is what the full adder is. I'm pretending this is the box for it. We said what, 3 inputs and 2 outputs. Here's my 3 inputs. This is A, this is B, and this is the carry C, right? I should put a space between them. There's my 3 inputs, and I have my 2 outputs. This is S, and this is the carry out. So these are the output here, and these are the inputs. I have 3 inputs, 2 outputs. Maybe I should move the S down there instead of right in this spot here. S and C. I'll just move them away from this. My plan is changing by the minute, because what I'm going to do is draw a line here inside of that. That's the A. And this is the A NOT. I'm going to put a NOT gate here. See the NOT gate? Can you see it? This is the B. This is the B NOT. And this is C and C NOT. And now I'm going to build each one. I need 4 AND gates for the sum and 1 OR gate. So the sum is going to have an OR gate here. That's an OR gate. Attached to it, 4 AND gates. So this is 1 AND gate for the sum. Another one for the sum. And they'll be ORed together. I'm not going to run the wires because it's going to get ugly. That's how the sum is going to be. What's attached to it? Again, this is A NOT, B NOT, and C to this one. This is A NOT, B, C NOT. This one, A, B, and C. And this one, what? A, B NOT, and C NOT. You have all these values, just attach them. I'm not running the wires, it gets ugly. And for the carry again, you're going to have an OR gate. And in the OR gate, we're going to have how many AND gates? 3 AND gates, right? And what's attached to them? A and C, B and C, and A and B. And that's your 1 full bit adder. So this is a full adder. This is what the inside of that looks like. Just take these wires from here, A attach it, C attach it, B and C, A and B, attach them right there to your gate, and you have a 1 bit full adder. That will tell you when the sum is going to be 1, when the carry is going to be 1. Now, just to take you back, I said you can go actually to the store. We can go to the company we buy our chips from and say, can you get me a 4-bit adder? Do you sell them? And they have them on a chip. And you take the chip, bring it home with you. It has 4 bits at a time. Now, if you want to make a 12-bit adder, the chip is already connected. It'll look like this when you buy it. That's what a 4-bit adder. I don't know if you can see it. That's the carry in. These are A, B, and C, the bits. This is the sum 1, sum 2, sum 3, sum 4 adds 4 bits, right? So if you were buying that, the first thing you want to do is attach this one to the ground. Because the first column you're adding, there is no carry. So if I was in the lab and I'm going to build this one now, I'm going to run it. I'm going to create a 12-bit adder. That will add 12 bits at a time for me. First thing I got to do, these will have to be powered just like any other chips that we saw in the lab. You got to put some power on them. You'll see when we go to the lab we have to power them. But beside the power, I need to make sure this is attached to the ground. That's the first bit. Some 1, some 2, some 3, some 4. This will be 5, 6, 7, 8, 9, 10. Notice the carry from this now. You don't ground that one because you're adding a lot of bits. So whatever carry coming out of this goes right there and continue with it. And that's the lost carry.
So pretty much
That's a 4-bit adder. 4-bit full adder.
and
Each.
And you add each and gate.
You just
to it.
the whole inside is made when you buy them. Each one of this will have 4 of these sets in it. 4 of them. But when you buy it, it has all the stuff already in it.
Mhm.
So all these gates are already inside that. And you got 4 sets of these in it inside each one of these.
Yeah, but how do they know you need A bar, C bar, and so on forth?
That's the truth table. That doesn't
Oh,
change.
you send them and they already make
No, that's how you add them.
This is what that chip always does.
Yep, it adds them this way. Doesn't matter. So you can play with the input yourself, but it's going to follow this pattern. What do you have attached to them?
Okay,
Yep.
I see.
But that doesn't change who's making it, you know? Now, if you want to do subtractions, if you remember when we started talking about algebra earlier, I said, you know what? I can put a subtractor, but we don't want to do that. Will be better if we do complements. Remember the complements? Instead of subtracting, you add. So this is what we do to a full bit adder to make it do addition subtractions. The first number, assuming the top number is the one you want to, the bottom number B is the one you want to subtract or add. Now, if you're adding that number, if you decide to add that number, then you put a 0 here. Because if you put a 0, let's see what happens. You have a 0 here. 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 Let's say my number, I want to add these numbers. I want to add 1, 1, 0, 1. I want to add to it 0, 0, 1, 1. You want to add, not subtract. Can you see that on the screen? Okay. I hate to write on the book, but here we go. 1, 1, 0, 1. I want to add to it 0, 0, 1, 1. So since I'm adding, I'm going to put a 0 here. So that's a 0 here. You can see the numbers here, right? So I'll make sure I write a little bit darker with this so I can erase it. Let me sharpen the pencil. So let's put these bits here. Bit 1, that'll be a 1. This is a 1. This is a 0, and that's a 0. Can you see them now?
Yes.
So if you're adding, you're putting a 0 here. So this is a 0. Because when you add the first 2 digits, the carry coming in is 0. Now let's see. That's exclusive OR. What's exclusive OR? If the numbers are the same, the result is 0. If they are different, the result is 1. So these numbers are what? Different. The result is 1 here. These numbers are different. The result is 1. These numbers are zeros. The result is 0. These numbers are 0. The result is 0. So you're actually adding 1, 1, 0, 0, and you're making the carry 0 for the first one.
Wait, so if they're the same,
Basic addition.
if they're the same, that means they're 0. If they're different, they're 1.
One, 'cause that's what the way this gate works.
Okay.
Now, if you were subtracting, let's think about subtraction. So it does work for addition. Everyone see that? Let's say I was subtracting now. Uh-oh. I broke the eraser.
You want here?
I got actually one here. Let's see. Does it look like it's gone?
It's good.
Yep, it's gone now. Let's see, I want to do a subtraction. I'll use red here for subtractions. I want to do 1, 1, 0, 1. I want to subtract from it 0, 0, 1, 1. Remember how we did that? We said the first thing we need to do with that number is do what?
Flip it over.
The 2's complement. The 2's complement becomes what? 1, 1, 0, 0,
Plus 1.
plus the 1, which will make it what? 1, 0, 1, 1, right? Then we add them. Well, let's see what will happen if you put a 1 here. If you put a 1 here, I use a pencil here. I got a 1 coming in. This one is this guy here. You'll see that. So this 1 here is going to be that addition of that 1 here to give the 2's complement. Let's see actually if these numbers going to be 0, 0, 1, 1. If it is, what this just did the 2's complement for me that I'm adding them. So now I got a 1 here. 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 And the numbers were what? 1, 1, 0, 0. That's what I'm subtracting, right? Minus 0, 0, 1, 1. 0, 0, 1, 1. Let's see what the XOR gate is going to do here. When these numbers are the same, the result is what?
0.
0. Same. 0, 1, 1.
Flip it.
Son of a gun, that's the 1's complement, doesn't it? 0, 0, 1, 1 is the 1's complement. Now we add that 1 to the carry, that makes it what? The 2's complement. And now we add them. So the same device actually is being used for addition and subtraction. If you put a 0 here, that's for addition, you put a 1 when you're subtracting. And that will take, oh, come back here. That will take care of the whole thing. So I don't have to have separate chip for addition, separate one for subtractions. This one does both of them. Subtraction and adder and subtractor. So we're doing subtraction with the same device. I figured I'll mention that. Let's talk about another device called decoders.
What was the one before called? Device before called?
This one's just a 4-bit adder.
4-bit add.
Yep. Let's talk about decoders. Now, decoders are very, actually, let me stop here.